I'm sorry, trying to slow you down. No, because you said it's not enough to say that just one single distribution, in particular the uniform distribution that you took, that's enough for.
Yeah, so that is not enough yet. So we will see what do we need extra for that, and towards that we will go to this interlacing. So that's exactly the same plan that I mentioned last time.
Okay, so you are going to say that if every
product distribution had this real rootedness, so for all these product distributions, all I need is that they're all real rooted. And then I also have this fact that one of the expectations, this uniform distribution, has maximum root 2 times square root minus 1. Together, these things will imply that one of the ASs has maximum root at most 2 times square root 2. So that's what I want to show now.
Okay, so you want to show that for every product distribution, things are at least real rooted.
Yes.
And together with what you have shown, this will apply. Okay.
Yeah. So let's start with the one simple version of this. So the setup is now this. So let f1 to fn be degree d polynomials. So univariate, degree d univariate real polynomials, so real coefficients with real roots. Oh wait, sorry, no, that's not. So with degree d, yeah, with real roots and positive leading coefficient. So the highest degree coefficient is positive in all of them. Okay. So suppose that they have a common interlacing. So what does that mean? So a sequence of numbers, alpha 0 greater than alpha 1 greater than alpha 2 greater than alpha 3, so on, greater than alpha d greater than alpha d plus alpha d, so just d such numbers such that if say beta I1 bigger than beta I2 bigger than beta I3, so on, beta IT are the d roots of F5. So this is all counted with multiplicity. So if some root appears multiple times, you will write it multiple times. So
I cannot hear. Is it just me?
Hello, I can hear Piyush.
Yeah. So then if this F, which is defined to be the sum of the F5s, has largest real root at most gamma, then suppose that then there exists I in such that the maximum root beta I1 of F5 is at most gamma. Okay.
Wait, did you define interlacing?
Yes, that's what the green thing is a definition. So a common interlacing is exactly a sequence of numbers alpha 0 to alpha d. Oh, oh no, oh, sorry. Yeah, sorry. Yeah. I got distracted in the. So yeah, so then what is the interlacing? So then these things lie in between. So alpha 0 is bigger than beta I1, is bigger than alpha 1, is bigger than beta I2, is bigger than alpha 2, and so on, all the way till alpha d minus 1 is bigger than beta I t, which is bigger than alpha d. Okay, so that's what a common interlacing is. So what is common about it? The point is that this alpha sequence is the same for all i's. Okay, so the same is it clear? So it's the same thing. So let me just sorry, what? Yeah. So this is the definition of interlacing. So the common vector says that. So I'll write another way of writing, which will look maybe slightly more reasonable. But this is the definition that is easier to use. So you have a common set of d plus 1 numbers, says that all the roots of, so if you take any fi, the roots of those, the d roots lie in the consecutive intervals that is d plus 1 numbers define.
Now, Piyush, if beta I1 was equal to beta I2.
Yeah, then alpha 1 will have to be equal to them.
Okay.
Yeah. Because you can see that it's sort of
In that case, it must be a common vector for the polynomial.
Yeah, exactly. So you can see that all these things are implied, right? So suppose if beta I1 is equal to beta I2, then you can get that somehow. Yeah. So all these polynomials should now have this double root, because otherwise there will not be a common. So common interlacing seems to be a pretty strong condition in that sense.
Right.
Yeah? So yeah. So yeah, so then it says that so suppose they have a common interlacing. Now suppose that the sum has largest root at most gamma, then there is one of the i's for which the largest root is at most 1. So then you can sort of do the probabilistic method. So sum here can also be made expectation. I mean, the adding weights doesn't change anything. So multiplying the polynomial by positive number doesn't change the fact that it is. So this is important, that they all have the same sign of the leading coefficient.
Sorry, Piyush, I have another question.
Mm-hmm.
So can you go to the next page once? Mm-hmm. So like if this, okay, this is the conclusion you're saying, but suppose instead of the largest, I said the smallest is at least gamma, then would you still be able to conclude that then there exists an I such that the minimum root of this is at least?
Yes, because you just apply the thing to the polynomials given by f minus x, right? So gix equal to fi of minus x. So now the roots are just the change in sign, so the order reverses.
Yeah.
And they now instead of positive, yeah. So now again, the positive leading coefficient is not important. What is important is all of the leading coefficients have the same sign, right? Because you can just multiply by that sign and make it positive.
Correct.
So yeah.
Piyush, is there a relation between D and N or not necessarily? Like
No. So no.
Okay. So D equal to 2 is trivial to get, but the more D you get, the more control you have. Is it like
so D equal to 2 is trivial to get. D equal to 2 is trivial to get, probably. Yeah. I mean, here also it's not be complicated. It's just changing signs. So it will not be it will be just a small argument. Probably the same argument that you have in mind for D equal to 2.
Oh,
okay. Okay, so now let's look at this. So now, let's look. So since fi's all have positive leading coefficients for large enough x, they're all positive, right? For all large enough x, they're all positive. Right? So in particular,
So those alpha is
Hmm.
are may not unique. Still, it will hold, right? We need to just get some alphas which will do the job.
Yeah. Maybe I should just write before the proof remark. So what does the common interlacing mean? So here is this thing which maybe sounds more reasonable. So define this interval. So what I call for the ith polynomial, the jth interval. What is this interval? So this is this is from beta I. So the jth root. Um, okay. For j equal to 1 to b minus 1 and I.
Taking the intersection of all such intervals.
Yeah, so all these intervals have to be essentially empty. So beta is 1 to infinity. They have to be non-empty. So and I minus infinity. Okay. Then fi. So this fi have a common interlacing if and only if for every j in 0 to d plus 0 to d, the intersection of all the jth intervals, all the polynomials, is non-empty. And and this is precisely so. What is this alpha j going to be? You will just choose alpha j from this interval. So this is just a different way of writing the definition, which maybe looks more reasonable because now there is nothing about these special values being said. It's just about the polynomials. So these consecutive intervals have a common intersection for every j. Okay. Is it fine?
Yes.
Okay. Okay. So right. So now let's start the proof. So the proof will be about is about chasing signs more or less. So the point is this. So for large enough x, for all large enough x.
Piyush, what is an example of a non-interlacing family of polynomials? Like just for understanding.
I mean, anything, right? I mean, like you just take some. I mean, interlacing is special. Non-interlacing is not special. I mean, you just just arbitrarily choose roots so that they don't this intersection becomes non-empty. So it becomes empty, and then make a polynomial with those roots.
Just two polynomials can be non-interlacing.
Yeah. Like just make both the roots of polynomial less than both the roots of the other.
Okay. Now I think I misunderstood the definition. Now I understand. Okay, all right. Okay, thanks. Yeah.
Yeah. So maybe graphically. So this is more graphic, right? So the point is that these roots have to be like. So we just change the colors here. So it makes more sense. So the roots of the polynomial have to lie within. Okay. So these guys have to lie within the consecutive intervals, the alpha x. That's the point. That's what these intervals are. Okay. Okay. So for all large enough x, fix is strictly positive, right? For every I. For every I. Okay, so now let's see. So we know that so in particular, in fact, this fi of alpha 0.
So sorry, Piyush, you are proving what? I got. I mean,
they're proving this result that so assuming that they have a common interlacing.
Oh, okay.
This fact holds that if the sum has the largest root at most common, then one of the i's has the largest root. Okay. So in particular, this fi of gamma 0 is certainly non-positive, right? And in fact, I can always choose, and we can in fact choose, and we can, yeah. So this is just to note that we can also choose alpha 0 such that fi alpha 0 is actually strictly positive. Okay, so this is just to know, right? Non-trivial, because you just if not, then you just increase alpha 0. The point is that after the largest root, all these polynomials are strictly positive, right? Because after that their sign cannot change, and at infinity, as the x goes to infinity, they have to become positive. So after their largest root, they will be positive. So you just choose alpha, and alpha naught has to be at least as much as the largest root of each of them. So you just choose it large enough. Okay. So so in particular, this f, so the sum is also positive, right? This is one thing. Now let's look at what happens at alpha 1. So my claim is that fi now this fi of alpha 1 is less than equal to 0 for every I. So notice, what is alpha 1? Alpha 1 is this number that lies between, that is just below the first root, but higher than all the other. So it's less than equal to the highest root, but bigger than or equal to all the other roots. Okay. So why is this true?
Sorry, Piyush, I'm a bit confused. So these alpha zeros were given to you, right?
Yes, because they have a common interlacing.
Yeah. But I'm saying, oh, okay, you just showed that. Okay, if you take the largest, correct. Yeah, okay, fine. Yeah.
Yeah, the largest one, you cannot always increase the largest one. That doesn't hurt you.
No, you just proved, because I was saying that what if the adversary gives you an adversarial interlacing, but that's not the point. The point is, because as you said, if you just take the largest root, right?
Yeah. And then increase it a little bit. Yeah, that's also valid interlacing. And yeah. So and now this fi of alpha 1 has to be less than 0. I claim. Why is that?
So between two consecutive roots, unless it is a double root, the sign will change.
Yeah. So if not, so if fi of alpha 1, so let's see. Suppose that fi of alpha 1 was positive. We know that fi of alpha 0 is positive. Then how many roots must fi have between alpha 0 and alpha 1? An even number, right? Because counting multiplicity, because the sign changes at each root. Again, counting multiplicity.
And there will be some issue with double roots.
Sorry?
There will be some minor issue with double roots, but
no, there's nothing about common roots right now, and this is not an issue.
Double.
Even double roots is not an issue.
You are counting with multiplicity.
You're counting with multiplicity. So the number of roots between 2 points, if they are positive, if the function value is positive at both points. So if fi alpha 1, so why? Because if fi alpha 1 is strictly positive and f alpha 0 strictly positive, then the number of roots of fi in the interval alpha 0 to alpha 1, alpha 1 is the smaller one. So this might be a degenerate interval also, possibly, is even. Right? If it is degenerate, then the number is 0, which is also even. Otherwise also, so this is counting mode. But this contradicts this, right? This contradicts the definition of.
This proof for this multiplicity thing you have, like, is there like an inductive proof you have in mind, or is it just by picture, or
Which one?
this fact that it is even?
Yeah. So yeah, I mean, yeah. So what's the proof for that? It's even. So actually, we will do this argument. But yeah, but let's see. So let me just write what was written.
Okay.
Okay, so let's see. So yeah, so what Siddharth was saying. So how do we do this? So this is fine. So as Shweta was saying, if there's no double root, there is no problem. So the only problem happens at roots that are that have multiplicity. Now, so how do you handle those guys? So at those guys, you just do a continuity kind of argument and see that, like, if it's a even degree double root, then the signs on the both sides are the same, and if it's an odd degree root, then the signs change. So you see what I'm saying? So
what do you mean by a degree of, meaning the multiplicity?
Yeah. So suppose that, so see here, polynomial R is a root, right? So now let's say that x minus r to the k is the highest degree, the k is the multiplicity of this root. Then if k is even, so k even, then it should be like this.
Yeah.
And if k is odd, so this is just a continuity argument. Right? So you just look at what is the function behaving like in a small neighborhood. And if k is odd, then it behaves like this. So at each root, the sign changes, especially exactly when the multiplicity is odd. So just by this, so is that fine?
Yeah. But I thought this was understood. What are we now?
No. So Siddharth was asking, how do you prove this? Is there just picture or?
Okay.
Okay. So right. So okay. So what do we have? So yeah. So this is thing. So we have that fi alpha 0 is fi of alpha 1 is less than equal to 0. F of alpha 0 is, and so this also implies that this f of alpha 1 is also less than equal to 0. Okay. So now what do we have? So f of alpha 1 is less than equal to 0. F of alpha 0 is bigger than 0, and alpha 0 is bigger than alpha 1. So there must exist. So this gamma, right? So the root gamma. So the maximum root gamma of f must be at least alpha 1, right? Because 1 implies that f has a root in the interval alpha 1 to alpha 0. The root could be at alpha 1 also, because this could be just 0. If it is not, then it is strictly inside. Okay. Okay. This is fine. So
Yes.
yeah. Okay. So now let's see. So now we have that f gamma is equal to 0. So this implies that there must exist. So there must be some I for which Fi of gamma is non-negative, right? Because if all of them were less than 0, then f of gamma could not be 0, right? Is it fine?
Yeah.
Okay. So so now, but notice that, but gamma is bigger than alpha n minus 1, and Fi of alpha n minus 1 we knew is less than 0. So Fi must have a root.
Piyush, gamma is not greater than alpha n minus 1. No? Gamma
Sorry, alpha 1.
alpha 1.
Yeah, alpha 1 in alpha 1 to gamma. Right? So in particular, that means that this beta I1 is less than or equal to gamma. Right? Because that is the root that is at least. So the root of Fi that is at least alpha 1 is exactly the root that we were calling its max. That is exactly the maximum root of Fi, right, by definition.
I got lost. I mean, the picture might. Wait a second. Let me.
Yeah. So let me just say about the picture. So what is the picture of Fi? So here is alpha I minus 1. Here is alpha 1, and here is here is beta I1. Right, and then thereafter that the Fi has no roots, right? And this alpha I1 could possibly be equal also, right? That's okay. Now what we are saying is that Fi, so here we know that Fi, so we know that here the value, so let me just ignore the equality. Here we know that the sign is negative. So here, so at this point, Fi of, so alpha 1 is less than 0. Okay. We also know that there is a gamma point. And we know that this f of gamma, we know also that
0, right?
Yeah. Sorry.
We have also alpha 0, right?
Yeah. So alpha 0 is somewhere. Yeah. So here, and here we know that it is positive. Okay. But we also know that Fi of gamma is also non-negative, and gamma is at least alpha 1. So gamma is somewhere here. Now, question is, can gamma be before beta I1? No, right? Because that would contradict that the only root of alpha 1 that is only root of Fi that is at least alpha 1 is this one.
Sorry, why do we know that Fi of gamma is greater than or equal to? So why did Fi change its sign by gamma?
Yeah, so that's the point. So because we know that f of gamma is 0.
Oh, right. There is at least
so there are at least one guy which has to be non-negative.
Correct.
Right? Not all of them can be negative.
You're taking that I, correct?
Yeah. So then we get that this. Right? So max root of. Okay. So
that's the end of the argument, right?
Yeah. So we somehow didn't seem to use the full power of interlacing, right? Only sort of the last few ones, right? So just alpha 0, alpha 1, right? And nothing else, sort of. So yeah, so in fact, because this the claim here is actually more powerful, so you can actually then show that this F0 is also real rooted fully just by doing this chasing in the same way. So yeah, so but
what is F0? Sorry,
this F, so their notation is called F0. So the sum is also real rooted. This F, it's the sum of the F's.
No, but I had the same issue as you raised. Like, where did we use the full? I mean, it's just the fact that the highest roots were.
Yeah. So that's what. So I'm saying that the assumption is powerful enough to actually show that F is real rooted.
For which you will need every.
Yeah, and then you will basically keep doing this argument at every level, and then that's.
But if we didn't want that, then this should be enough, is it? Yeah.
So then we will, I think, or we will just need sort of the interlacing of the top, something like that.
But without interlacing, you don't know if F has real roots.
Which what has what? So I don't need that f as real root. I never use that f as real roots. I just use that its largest real root is at most common. That's all.
Okay.
We never use that f is real rooted. Right? So in fact the one root we wanted, we actually constructed it because we saw that, well, for all large enough x, f(x) is positive, so f is also positive. And then there is a point where all of them are less than equal to 0. So between that, f must have a real root.
Right.
And for that, all we needed was this fact that there is this one alpha, this sort of interlacing of the top roots or something like that. So this for top two roots with this. Okay, so but this is fine. So this is thing. So now the question is, how do you show that some polynomials have interlacing, and what is this interlacing thing good for, etc.
So
Is there any
one remark. Sorry. So we have not yet come to this MSS paper proper yet, right?
This proof is from MSS. Yeah, that's it.
Oh, the interlacing idea was
No. The common interlacing idea has been present before, and this lemma is also present before. But yeah, this form of the lemma they need to use.
Huh? This what?
Form of the lemma they had to use, and I mean I'm sure this might have been there in the literature earlier also, but yeah.
Oh, okay.
Yeah, common interlacing is the older idea. It's not. So their idea is to go use this interlacing idea to do this kind of probabilistic method type argument.
So to look at the probabilistic, so look at the
like use it to bound maximum roots in this way.
Okay,
Like,
that was not there.
like find one guy with this. So in this form, I think they were probably first to use it in full power.
So you said that if I change with the, if I take summation CI where CIs are non-negative, positive strictly, then also it's fine. The result
Yeah.
holds, right?
I mean, nothing changes, right? I mean, all the polynomials still have their same roots. So whatever the common interlacing was remains a common interlacing. That's it.
Yeah.
And
So is there any result for regarding products also? If we take the products of FI?
I mean, products is easier, right? Because the roots of the product are exactly the union of the roots of the original one.
Okay.
So the roots of the product of, so if you take a product of f1 to fn, then the roots are exactly the union of the roots of the fs.
Yes. Yeah.
So okay. So right. So now So now so we have this. So now let's go towards actually proving first, understanding how one proves that that one can get interlacing. So just make sure. Yeah. Okay. So interlacing is good. So how do we get interlacing? So so let's concentrate on the case of two polynomials first. So n equal to 2. So here is a lemma that let f be let f1 f2 or let fg the integrity polynomials with positive leading coefficient. Suppose that lambda f plus 1 minus lambda g for every lambda in 0 1, or actually, so I just let me choose af plus bg for every ab non-negative is real rooted. then F and G have a common interlacing. In fact, it's a if and only if condition, but we will only use. Okay, so this is one of their also. So this again is an old lemma. Their sort of one of the innovations of MSS is to use this. So basically, they show like they find a way of coming up with showing that some of these sort of these not positive linear combinations are real rooted, and thereby getting these interlacings. Okay. But this lemma is again well known. So the proof I will do is so there are many so proofs are basically chasing signs, most of them, and they use also the continuity of roots. The one version I will do is from Chudnovsky and Seymour on for the paper on the independence polynomial of claw-free graphs.
Oh, so this Chudnovsky and Seymour graph theories, they have used interlacing now.
Well, yeah. So their paper is this thing. So so what is their so this paper is called the independence polynomial independence. So it's on the independence polynomial of claw-free graphs. So what is this? So what is the matching polynomial? So the matching polynomial is exactly the independence polynomial of a line graph. So independence polynomial is a polynomial which is what exactly sounds like it. So for every independent set in the graph, you put so every independent set of size k, you put a lambda to the k and sum it up. So the matching polynomial is like the independence polynomial on the line graph, where the nodes are the edges, and the edges correspond to two. So two edges are connected if they share a common vertex. So that's called the line graph. Now, like not every graph is a line graph. Right? So line graphs have a lot of structures. So they cannot have claws, but also not all claw-free graphs are line graphs. So what they showed is that the Heilmann-Lieb theorem about the real rootedness of the matching polynomial actually generalizes to the independence polynomial of any claw-free graph. So that's what the result was. And so in fact, so I didn't do this, but
I'm just curious about one thing. So before this, I mean, I'm just wondering, because Chudnovsky and Seymour, in my understanding, is they're like pure graph theories, not necessarily working with algorithms. So why would a graph theorist be interested in showing before the MSS result about the real rootedness of a polynomial?
No, because yeah, I don't know. I mean, the Heilmann-Lieb is a pretty interesting thing. So I mean, for example, you get all this concave. So I mean, one thing that commenters are always interested in is proving that some sequence is log concave, for example. So the real rootedness implies that if the generating polynomial is real rooted, then the corresponding.
Commenters are interested in it not just for the purpose of sampling or something.
No. Yeah, I mean, yeah. So one of the things that they're often interested in is log concavity of sequences. So that is one reason to be interested in real rootedness. I don't know what Chudnovsky's exact motivation was. Yeah, but the paper is nice. It's a short 11-page paper. So I didn't mention this, but actually the Heilmann-Lieb theorem, their proof of the real rootedness of the matching polynomial is also based on interlacing. So I didn't do this, but yeah. So in that sense, interlacing is really old idea. So the proof we did was slightly different, right? But so the proof I'll do is from this, but it's older. Okay, so yeah, so let's do this. So so the first thing we will do is the following. So the first is we'll prove another lemma, which is maybe show why this kind of a thing should be true. So suppose, so FG, so again, are in the, so let me call this lemma star. Okay. So suppose FG are as in lemma star. So that means that they are degree D, positive leading coefficient, and every positive linear combination is real rooted. Okay. let A less than B be points where F and G are both non-zero and have the same sign. Which means that FA times GA is positive and FB times GB is also positive. Okay. And define for any polynomial P and any point T in R, NPT is to be the number of roots of P in the interval from T to infinity. So that is at least T, and this is counting multiplicity. Then the thing is that NFB minus NFA is equal to NGB. So notice it is not. So what are the conditions? The conditions are F source is slightly more generic, but we don't need it. So F and G have the same degree positive coefficients. The important thing is that they have this property that any positive. So this is the important one. Any positive linear combination, any non-negative linear combination is real rooted. In particular, they themselves are real rooted, and any non-negative real combination is also real rooted. Okay.
Can't hear you, Piyush.
Sorry. Yeah. No. Is it fine? So is the statement clear? Can you hear me now?
Yeah, I can.
Yeah.
It's just that, sorry for nitpicking. This AB, okay, so yeah, anyway, I mean, the AB there appears coefficient.
Oh, sorry. Okay. Yeah. Let me call something else.
If you just change it by something. Sorry. Yeah. Sorry.
Yeah, that's fine. Yeah. It's confusing.
So the left hand side is the number of roots of G in A comma B, right?
Yes, but yeah. So the B side is open, right? That's
Yes. Closed open. We closed
Yeah.
A open B.
Yeah.
Right?
Which is fine. I mean, you can even close it because we assume that anyway they don't have roots at B. Yeah. So A and B are roots of neither F nor G by definition, right? Because we assume this. It's the same signs. Yeah, and that is in fact the proof, what Shweta just said, right? So NFB minus NFA is the number of roots of F. So it's really this, but this is equal to the number of roots. Because FA is not 0 anyway. And similarly for G.
Understand. How is that the root? How's that the proof? Sorry. This is
So I'll say why that is a proof, but you need just one more observation.
Oh, because the signs are always the.
No, the point is that yes, let's just do that. So we have not used the main part of the hypothesis yet, right? That all positive linear combinations are real rooted.
Yeah.
So we have to use that also. plus FG is okay, but now let's look at this. So consider this polynomial PTF, which is just P lambda fx plus 1 minus lambda gx. Okay, lambda in 0 1. Okay, P lambda is real rooted. Okay, and this is the crucial thing. The roots of P lambda. So this you should think about this question, this sentence, if you have not done this condition before. The roots of P lambda are continuous functions in lambda. Continuous functions of lambda. What does that mean? It means something like this, that I can define n functions, or rather whatever the degree is, d functions, okay, R1 to RD in lambda, such that R1 lambda, R2, so all of these functions are continuous, and Ri lambda is the ith root of P lambda, or Ri lambda is the root of P lambda, and for every lambda there are a complete set of roots. Okay, so that's what it means, that the roots are continuous functions.
Sorry,
So
please, can you repeat that once more?
Yeah, so what I can do is I can define d continuous functions, R1 to RD. Functions from, so there.
What is D? D is the number of roots.
D is the degree of these polynomials, f and g. So I've defined these d. So these functions are supposed to be the roots of the polynomial P lambda as lambda varies. So all I'm saying is, I mean, the point is that when you talk about roots, so sometimes the roots can cross and all that. So you have to be a bit careful about how you're defining it. But the point is that that doesn't create a problem at all. So all you're saying is that you can define these d functions, R1 to RD, functions of lambda, such that each Ri lambda is a root of P lambda, and R1 lambda, R2 lambda, R3 lambda, R4 lambda, so on till RD lambda are the complete set of roots of P lambda. So this whole vector is continuously changing, and it's
where did you specify the continuity?
Yeah, this is just a fact from analysis, and it can be proved.
No. I'm just saying. I thought you were specifying the meaning of the statement that the roots of P lambda are continuous functions of lambda.
Yes.
And the meaning is from
that this whole, you can define this d length vector that is continuous in lambda, and which is always the set of roots of the full set of roots with multiplicity of d lambda.
Piyush, why is this not in contradiction with this Galois theoretic arguments that we can't track a root continuously?
What is a Galois theoretic argument that cannot track?
Like you can't have a solution of the quintic basically because you can't give a function which tracks one of the roots. You need a branch. The function should have a.
So that uses
no, but that is not about
only
continuity.
Radical expression.
It's only about radicals.
No, this is inverse function theorem, right?
Yeah, this is essentially, yeah. So this is either you can inverse function theorem or even less.
So sorry, Piyush, can you spend one?
Or implicit function theorem. Yeah. Mm-hmm.
No. I mean, sorry, can you again say what is this you're saying?
So I'm saying that there is a vector of, so one other way of saying the same thing that I was saying, there's a vector of dimension d, and every coordinate of this, or this whole vector is a function of lambda.
It's a continuous function of lambda.
A continuous function of lambda.
Yeah, because that thing is, okay.
Yeah, and this vector has the interpretation that at any value of lambda, these d coordinates are exactly the t roots of P lambda counted with multiplicity.
Okay. Yeah.
So continuous does not mean solvable with radicals. So that is. Yeah.
So I'm sorry, but I'm a bit confused because you said we have to be careful in understanding the meaning of this statement. But
yeah, because so the only thing is that you have to be careful in the sense that so you suppose you start tracking the root R1 and it start tracking the root R2. At some point they might become equal. So then you have to decide. But all I'm claiming that is not really a problem. I mean, you just call one of the branches R1, another branch R2.
So all you are saying is basic. Aren't you therefore just saying that, or is this? So if I just looked at, I see. Okay.
Yeah, I mean, this is not a very non-trivial. I mean, it requires some thinking. As I was saying, you can do implicit function theorem kind of thing to prove it. but yeah, that will even give you differentiability quite often, like in many places. So, but except at double roots. But the point is that, yeah, I mean, if you think about it intuitively, it's very clear, right? You have this graph that is continuously varying, so its roots can also change only continuously. Like where it intersects, so you have a graph and it's changing continuously as you change lambda. Like so where can the intersection of the line go?
No, but isn't it? I mean, so can't we just sort of order the roots and say that, okay, let's look at the largest root of.
Yeah, so that is one way. So, but the thing is that this is true even in complex numbers. This fact, and then the largest thing is not maybe. Yeah. So yeah, so this is true even for complex roots. We are just using it for real roots.
Yeah, because you said P lambda is real rooted, right?
Yeah. So yeah, this does not require the real rootedness. This is just a.
So basically, you are taking a continuous path from F to G, right?
Yes. Yes.
And each root of F is approaching to each root of G as lambda approaches from 1 to 0, right?
Yeah, but we don't even need that level of detail. Now we are more or less done, because the point is we know that neither F nor G have a root at A or at B. Can any P lambda have a root at A or B?
No.
Yeah, because of the same reason, right? Because both F lambda and G lambda have the same sign at A and B. So note that for every lambda in 0, 1, P lambda A is not equal to 0 and P lambda P is also not equal to 0. So these continuously varying roots, which happen to be inside this interval AB, can never go outside it. Because if they happen to ever go outside, they will at some point have to become A or B. That they are not allowed to do.
There will be a discontinuity.
Yeah.
They will have to jump because.
Yes, and that discontinuity is not allowed. So this means that all the P lambda, by the continuity of roots, all P lambda are the same number of roots.
But is this assuming real rootedness, continuity, jump?
No, that's what I said. The root, yeah, so the continuity does not require real rootedness. But now because I also have real rootedness, I only have to care about continuity on the real line. They cannot jump and go through the complex plane, because anyway they're not allowed to jump outside the real line.
How
That was the hypothesis.
Sorry?
Go ahead. So that was something.
I was just saying that was the hypothesis, that AF plus BG is.
Yes. That's why the real rootedness is being used.
Okay.
Yeah.
But sorry, I lost some. Why do we know that both f of A and G of A is not equal to 0? I mean,
that was the definition. That was the hypothesis, right? So A and B are points where both F and G have the same sign and they are not 0. So FAGA are positive, FBGB is positive.
No. This A and B is okay. Suppose
so I'm saying for any arbitrary points A and B for which F and G are both non-zero.
Oh, that's the hypothesis. You have assumed. Yeah. Okay.
And now you're done. So the endpoints. Okay. So as soon as you find 2 points where they're both non-zero and they agree in sign, the number of roots have to be the same in that interval. So this already looks like something from which we should be able to.
So the upshot, the proof, therefore, basically just is saying that, okay, so if 2 points A and B, they are non-zero and they have the same sign, right?
Mm-hmm.
And for every linear combination, they remain real rooted.
Yeah.
Then basically, at every point inside this interval, right, A and B, in fact, every
Every
convex
p lambda has the same
combination,
number of roots. Yeah.
every convex combination of polynomial will have the same number.
Yes. The real rootedness was important. Yeah.
Although to begin with, we didn't even know whether f and g had the same number of roots in this interval.
Yeah. But now we've shown that every convex combination.
It's
And
a little bizarre.
no, I mean, it's not really. I mean, yeah, because the point is that this, the fact that they have the same sign and everything is real rooted, it's a pretty strong assumption. So,
But you assume that they have the same sign at just these endpoints, right?
Yeah. And I also assume that they are. So basically, what this saying is that if they have the same sign at the real root, they have the same sign at the two endpoints of the interval, and there is some convex combination where the root actually. So what can it do? So f is real rooted, g is real rooted. So at some point the root has to jump. So at some point the root will have to come to a, or cross over using the complex plane.
Right.
And neither of those things are allowed. That's okay. Is this fine? So, but
how do you prove that the roots of p lambda are these continuous functions?
Yeah. So how do you prove that the roots of p lambda are continuous functions? So one way of So there are many possibilities. So so you want to show that they are continuous in the complex plane. So the simplest one is
suppose I want to show just in there, because you have assumed this to be completely real rooted, right? So
so real rootedness does not help, I think, much.
Okay.
So just complex numbers.
Inverse function theorem works.
Yeah, so inverse function theorem or implicit function theorem. So those are the generic things which will just do it. And they will in fact even show differentiability at most of the points, like unless you have double root, basically. So so these are like forms of the inverse function theorem in some sense.
So in some sense here again,
I mean, in the complex setting, the simplest proof will probably go through essentially just the fact that so by the Cauchy integral formula, that's probably the best. Right? So for any analytic function, the number of zeros inside any. So you take any curve. So that's, let's say. So you take any curve gamma in the complex plane, and f is some analytic. So polynomials are an analytic. So suppose that f has no zeros on gamma, then the number of zeros inside gamma is the integral of f prime gamma is 1 over 2 pi I times the integral of f prime z over fz dz, where the integral is over this gamma. Over the contour. And you can show that these f prime z and fz also behave continuously. And this thing is actually an integer valued function. So if you change f prime z or fz slightly, this number can only change by a slight amount. But the slight amount has to be 0 because it has to take integer values. So that's what I'm showing. The number of roots remains constant inside any curve, and so by that you can get continuity by just taking this region to be small. Yeah, so that's probably the easiest proof just for polynomials. Yeah. Okay. So the rest of it will not require any analysis. It will just require now sign chasing. So let's continue with that. So the next observation, this will be now that we define this function, is the following: that if f and g have degree d and positive leading coefficient. So I'm not requiring that convex combination thing anymore. Leading coefficient. And
Piyush, just the previous argument that you were giving, this
Yeah.
Cauchy thing,
Mhm.
is that is true for multivariate polynomials also, right? The roots will vary continuously with the coefficients.
Yes, yeah. So that I think the easiest way to prove, yeah, that is true. Yeah, that is true for multivariate also.
Okay.
Yeah. Yeah. So the way I was doing it, you will have to do it by fixing everything and then doing changing one variable, that kind of
Okay. Yeah.
thing. Okay. Yeah. I mean, yeah, I'm pretty sure if you think about it, you can come up with many more different ways of doing it. Yeah. So nfx minus ngx is less than 1 for every x. Then f and g have a common interlacing.
Can you just go to the set of when you define NFA? Actually,
Yeah. So nfx is just the number of roots
yeah, number of roots that's with counted multiplicity, right?
of f in so which is at least x. At least x, which is the same as the size of is number of roots of f in x. So all of this counted with multiplicity.
Yeah. So you wanted to prove that that NFA minus NFB equals to
That we have done.
infinity,
That we
right?
have proved already.
Yeah,
Now
but
I'm just making another observation that
okay,
all
so
we need in this terms of this nf thing is to establish that the number nfx minus ngx never goes below. So it's always at most 1. So it's this absolute value is at most. It's either -1, 0, or 1. So if it is the case that at every x is either -1, 0, or 1, then the f and g have common interlacing. Okay. So how do we prove this? So let's assume. So is this clear to everyone? Or so let's assume that yeah. So let's assume that f there's a so we start at sort of infinity, right? So at infinity, what is nfx minus ngx? What it was like. So at a very large x, what is nfx minus ngx?
Zero.
Is 0, right? Because for very large x, both f and g are positive, always. So for all large enough x, f and g are always positive. So it's 0. Then you start moving towards minus infinity. At some point, you hit a root. Let's say that this root that you hit is a root of f. Okay. How does nfx minus ngx change?
-1.
Yeah. So so whenever you hit a root of whenever you hit a root of f, it increases by 1, and whenever you hit a root of g, it decreases by 1. And let's say we have ordered the roots. So the simplest way to do this is So
This is
the simplest way to do this
obvious
is
statement, no?
sorry.
This is almost an obvious.
Yeah, exactly. So yes, that's why writing the proof is a bit tricky. So the simplest way to do is to actually just think of sequences. So the only thing you have to be careful about is how you write the roots. So in fact, the only thing you have to be careful about is what happens when there are shared roots and double roots and all that.
Right.
So you just make sure make the following point. You write all the roots in this decreasing fashion, decreasing order. And now you have to label each root. So if it's a root only of f or g, you have no choice. You just label it with f or g, whichever it has. But if it is a double root, then if you have a choice, so suppose you have labeled the first I roots and the I plus 1th root, you have a choice to choose between f and g. Then label it with the different, like was if the previous thing that you labeled was f, label this one g, and if it was g, then label it as f. So you see that what I'm saying. So try to alternate as much as possible. If it is possible to alternate. That's the labeling scheme. Okay, and now you again do this. So you start at the plus in positive infinity. You hit the first root. Let's say our assumption is that the f is the first that you hit. You just change f and g. So now this increases by 1. Now the next root that you hit cannot be a root of f, right? Because if it was, nfx minus ngx will become 2. So it must be a root of g, right? and then the next root. So now it has become 0. So now you put the convention that whenever at any x where you first become 0, you will make that as an interlacing point, and you just keep making these interlacing points, and then you just show that this is a valid interlacing of f and g. Okay, so yeah, so just
Is the converse true?
yes, the converse is also true, which is, and just probably again it's sort of easy, right? So the point is that you just, so you whenever, so you just again do the same argument, right? You start from the plus infinity, it is 0, 0, 0, 0. At some point it becomes 1, and then before, until you go below alpha 1, nothing can sort of change it. So I mean, could you see what I'm saying? So at the first time you hit a root, it will become 1. Then the next time you hit a root of f, before that you have to hit a root of g, and so on. But the only thing to keep in mind for this argument is to label things properly, so that you don't get into a situation where there are 2 roots of f and then 2 roots of g, because all of these roots are the same. So whenever you can alternate, you alternate. That's the point.
No, so sorry, I thought it was okay. Now I'm a bit confused myself. Okay,
Mhm.
so suppose the first point is f. Yeah, the first
Mhm.
root that you hit
Mhm.
when you're moving towards the left from the right, the largest to the smallest, yeah, was exclusively that of f. Okay,
Yeah.
and then the next root that you're getting is a shared root of f and g. Of course, you labeled it with g.
Yes. No,
Yeah.
but then so you label it with g. Now it has become 0. You make g as an interlacing point.
Yeah.
Now you hit the root of f again, the same root again.
No, you hit the interlacing point is how do you find your alpha 0? Where do you place the interlacing point?
That root of g, that is your interlacing.
But
So at any x, whenever you are moving, and as soon as your x this difference becomes 0, you make that as interlacing.
Okay. Yeah, it works out. Yes.
So you can also do this by induction. Yeah. So this is just a sketch every time. Every time the difference becomes 0. So that's roughly what you have to. So this is not a formal proof by any stretch, but yeah, but you can just make an inductive argument out of this. Okay, so all we have to show now is that using these, so this is the result we'll use. The second one we have to use, so we have to just show that if f and g are as in the lemma star, then at every point x, fx minus gx, this nfx minus ngx is at most 1 in absolute value. Okay, so now we have to prove that. So the final lemma. Oh, okay. If f g are as lemma star, then for every x, is less than Okay. So the proof of this will be induction on the degree.
Sorry, what was the star condition again?
Yeah, so star condition is f and g are of the same degree d. They have positive leading coefficient, and every non-negative linear combination is real rooted.
Okay.
So induction on. So case 1 is degree d equal to 1. So d equal to 1 is easy, right? I mean, in this case, I mean, nothing can, I mean, it's just true, right? I mean, nfx minus ngx is just less than equal to 1. That's fine.
Even without the star condition.
Yeah, I mean, yeah, the star condition, yeah, because they're real polynomials, the star condition is automatically satisfied.
Are we going to use strong induction?
I mean, what is strong induction? So yeah, I'll assume usual induction. I'll assume that everything is true up till time d minus up till step d minus 1, and show that. So d equal to 1 is trivially true because f is like something like let's say so f is some cx plus cx minus d, some c times x minus r1, c1 times x minus r1, g is equal to c2 x minus r2, c1 c2. So for every x minus g. Okay, so so d equal to 1. So now suppose that this is true for, so assume that statement is true. Common. So now consider, so let now f and g now, so the induction, now let f and g be of degree d. So this is the inductive step. Okay, and suppose if possible, that there exists x naught such that nfx naught minus ngx naught is bigger than. So I'll relabel f and g if it's the other way around, right? It's greater than equal to 2. So let x naught be the largest such. So among all these x naught we satisfy this. Okay. Largest value that satisfies it. So what can you say about such an x naught? If it is the largest x naught that satisfies nfx naught minus ngx naught is bigger than equal to 2.
The next root is also a root of g.
Sorry, root of?
Root of g, right?
It must be a root of f. Right?
F.
Yeah, it must be a root of f, because if it is not a root of f, if f naught is not a root of f, so I can just increase it a little bit and it'll still not be a root of f by continuity. Whatever, by nothing, just because of Archimedes property. So I'll still not be a root of f, and the value will remain the same because like the root of g can only drop, and root of f has not changed. So this property will continue to be satisfied. So x naught is certainly a root of f. Okay. So right. So okay. So then let's look at so then x naught must be root of f. Okay. So now let's look at the derivatives. Let us now consider f prime and g prime, which have degree how much?
b minus 1.
And they also satisfy lemma star, right? Why?
Mean value theorem.
Yeah, mean value theorem or Rolle's theorem. Yeah, and also satisfy.
Between any two consecutive roots, you can find the root of the
So
derivative.
so the point is that if AF plus BG is real rooted, then so if a polynomial is real rooted, its derivative is also real rooted. So in particular, if all the positive linear combinations of f and g are real rooted, then all the positive linear combinations of f prime and g prime are also real rooted because they are just derivatives of positive linear combinations of f and g. So and also satisfy star. So by induction hypothesis, n f prime x naught minus n g prime x naught is less than or equal to 1. But what is this nf prime x naught? Now, x naught is a root of f.
Sorry, Piyush, why did you get the less than equal to 1 now?
By induction hypothesis, because they are of degree d minus 1.
Oh,
Right?
So we know that the roots of f prime and g prime actually interlace, right?
Yeah, but we are not assuming it. I'm just saying. So right now, our only induction assumption is this. Yeah, so we also know interlacing, but yeah, let's just stick with this. But let's look at something else. What is this n? How many roots does f prime have in x naught to infinity? Now, x naught is a root of f, and between any two roots of f, this one root of the derivative. Right? So that's this interlacing. So in fact, this number must exactly be n f x naught minus 1 because we are starting at a root of 1, root of f, right? So whatever number of roots f has in that whole interval, f prime will have 1 less. Okay.
is this true even if there were repeated roots of?
Yes, because yeah, so the Rolle's theorem works also again by the same thing. So if you have a repeated root of f, so in that interval, the derivative also has a root, right? Because repeated root has to be a root of the derivative. So once you count with multiplicity, it's all fine. And g doesn't have a root, so it can have, but it cannot have more roots. So this will say, so what does it say? So nf, so nf x naught minus ng x naught is equal to nf prime x naught minus ng x naught plus 1 is less than equal to. Right? So this doesn't quite give us a contradiction, but it does tell us that this greater than equal to 2 cannot actually be greater than 2. It cannot be 3, right? This I will call 2 and this I will call 3. So 1, 2, and 3 imply that nf x naught minus ng x naught is less than equal to 2 certainly. Okay. So imply that that the only possibility remaining is that is equal to only sort of the bad possibility remaining. If it is less than equal to 1, then we have nothing to prove, right? I mean, so yeah, actually, by definition of x, so this is the only possibility remaining. Okay, is that clear? So let's see why is this. So x0 was chosen for that, so that it's the difference between the values is at most 2, is at least 2. Then we showed that the difference between the values is less than some number that is at most 1 plus 1, which is at most 2, right? So so it's greater than equal to 2, less than equal to 2, so it has to be equal to 2. Okay.
Yes.
Okay, good. So now, so now we are sort of done, but let's just see one thing. So now notice that. So the point is that it's still possible that it's okay. So we have this. So we are in some reasonable shape now. Let's just see why. So. So okay, so let's see. So how can we use this? So notice that because both f and g have positive coefficient, there is some y naught such that nf y naught so that both f and g are positive. So this is of course greater than x naught. Positive for all y greater than y naught. Okay. So in particular, nf y naught is minus ng y naught is equal to 0, right? Because they're always positive. There are no roots after that, and there is. So this is all fine. Now, what we would like to claim is that this is a contradiction. Why? Because so notice that at y naught they agree in sign, right? And we would want to say that they sort of so notice that this is an even number, right? So okay. So what happens? So you have a function f. Whenever you cross a root, your sign changes. So I'm even saying at double root your sign changes. But if a double root, it changes twice, so it remains the same, right? So your sign changes exactly as many times as the number of roots you encounter. So as you are moving, right? So you start at y naught, which is not a root. You keep moving until you get to x naught. So your sign has changed exactly. So the sign of f changes exactly nf x naught times. Sign of g changes ng x naught times. So the sign of so the difference between that is even. So they both must still have the same sign. I mean, the only problem is that they can be 0 also. I mean, x. In fact, we know that x naught is actually 0. So there is some issue about that. Otherwise, we will get a contradiction, right? Because now if they had the same sign, so the goal. So if we could now find if we could now say choose a point, let me call it x1, just less than x0, so just little bit less than x0. So x1 is like x0 minus epsilon, or epsilon small enough, such that nf x0 minus ng x1 is also equal to 2. Then we would get, so this is the thing, if we could find this, then we would get
a contradiction, right?
Yeah, to what the first lemma. So then we would get that.
No, because we chose x1 to be the maximum, x0 to be the maximum. Oh no, that's right.
Yes, that's fine. Yeah.
So which
so
what is the contradiction there?
So if we could choose a point, so if we could choose a point x, just a little bit x naught. So what is the problem? So I choose a point x naught. So such that this is still true. Then what you would get is that is small such that fx1 not equal to 0, gx1 not equal to 0, and this equal to 2. Then you would get that fx1 and gx1 have the same signs. Because they have both had the same parity of sign changes starting at y0. And this is because of this factor that this 2 is even. Same parity.
But what is that a contradiction to? Piyush?
Yeah, so we will see it. So the same parity of roots in x1 to y0, right? And why is that a contradiction? That's a contradiction because, but then what do we have? Then we have fx. So they are the same sign at x1. So this is positive. We have by construction fy0 gy0 positive, and nfx1 is minus nfg1, sorry, ngx1 equal to 2, and nfy0 minus ngy0 equal to 0. And this is a contradiction because this is a contradiction to the so this would be because we have not yet found.
Yeah, because we have this will be contradiction to the lemma we proved.
Yeah, to the fact, yeah, the main lemma, the fact that this nfx1 minus ngx1 is equal to nfy0 minus ngy0 under these conditions. Is fg satisfied conditions of star and have had x1. So why can't we do this right now? Because the only thing stopping us is that x0 might also be a root of g. If it was not a root of g, then just moving a little bit will be fun. Okay. So the only problem in implementing this strategy is that x0 could be a root of g as well, and so ng x0 could also change in some weird way, possibly, right? So you just by moving a little bit to the left of x0, it's not that ng x0 is not changing. So we cannot just say that this remains 2. That's the only problem. But this is easily fixed. So how do we fix this? So we just kill off all the common roots right away. So what we do is, so this we do by saying that, but this we solve in the way that if, so you just take if f g have common factors, common roots. So this is factor out all the common roots. So this is fixed by. So this can only decrease degree. This can potentially decrease degree. Decrease the degree of fng by the same amount. And note that by the same amount, but by the same amount. But still keeps the conditions of But so the 2 points still keeps conditions of lemma star intact, because whatever is a common factor is also a common factor of all the linear combinations, so that's just fine. And importantly, and keeps the value of nfx minus ngx unchanged at any point whatsoever. Right? If you just remove common factors, nfx minus ngx cannot change, right? Because whichever root you have removed is counted both in nf and in ng. So the subtract is good for every x. So if the degree has decreased, all the conditions true, then you just apply induction hypothesis. If the degree has not decreased, which means that there is no common factor, then x naught cannot be in particular a common, can be a root of g, and so the previous scheme could work. So if x naught is a common factor, okay, we can just apply the induction. We can just apply induction hypothesis after removing the common factor, common root. Induction hypothesis after removing the common factor x minus x naught. Otherwise, we implement the other. Otherwise, if x naught is a root only of f, we apply the strategy of choosing x1 as before. And this completes the induction. Okay, so sorry, as it got stretched a bit longer than usual today. So any questions?
This what